Okay, guys, so we're starting chapter 3.1, which is the section on polynomial and rational functions. And we're beginning by looking at the polynomial function and models. A polynomial function is defined as a function f of x equals to a n x to some power n, and then it goes in descending order a n minus 1 x to some power n minus 1 plus all the way down to plus a 1x plus a 0, where an minus 1, a1, and a0 are constants that are called the coefficients of the polynomial. When the power is greater than or equal to 0 is an integer, and x is the variable. If that power is not equal to 0, it is called the leading coefficient. The leading coefficient. And n, of course, is the degree of the polynomial. So they're saying that this term here is the leading coefficient, and this is the degree of the polynomial. The domain of the polynomial function is the set of all real numbers, so negative to positive infinity. The leading term, that whole leading term right there, is an x to the power n. And the term a0, that term right there, is called the constant term. The polynomial in the standard form, we refer to this as being in the standard form if the terms are in descending order. Or in descending order. So, for example, polynomial 3x to the power 4 minus 4x to the power 2 plus 2x minus 19 is in the standard form. The graph of a polynomial is a smooth, unbroken curve. By smooth, we mean the graph does not have any sharp corners or any holes in it. So polynomial, not polynomial. Not polynomial. Now, keep in mind that it's specified that the power has to be greater than 0, equal or greater than 0, and is an integer. So in this example here, we are asked to identify the polynomial functions, determine which of the following are polynomial functions. For those that are, state the degree. For those that are not, explain why not. Write each polynomial in the standard form, and then identify the leading term and coefficient. So right here, this is a polynomial because all of the powers are positive and they're integers. So polynomial, and this is already in the standard form. The degree of the polynomial is the highest power here, 2. The leading term 3x squared, and the constant term is negative 10. Negative 10. Okay. SF, of course, means standard form. Here we have something that's not a polynomial because the power is not an integer. So, not a polynomial. Since n is equal to 2 over 3 is not an integer. Again, this power is negative, so it's not greater than 0, n is equal to negative 3. So not polynomial since n is equal to negative 3, which is less than 0. And finally, to see the polynomial here, we would probably want to go ahead and distribute. This is 3 2s or 6s to the power 3 minus 3s. So this is already in descending order. It's in the standard form. It is a polynomial. It makes the definition of a polynomial. And the leading term is 6s to the power 3, and the constant term is equal to 0. So things to keep in mind here: if the power is negative, or the power is a fraction, or the power is not an integer, then we do not have a polynomial. Immediately we know that. Moving forward here, the definition of a power function of a degree n is a monomial function in the form f of x is equal to ax to the power n. Monomial, of course, being a single term, where a is a real number, a is not equal to 0, and n is an integer. Notice that we could define the polynomial as a sum of power functions. So, for example, if we have a series of a power function, say 3x to the power 5, and then we have 9x squared, and then we have 8x, negative 8x, we can define a polynomial function as the sum of these, which is 3x to the 5th power plus 9x squared minus 8x. But it's important to know the power function is simply a monomial term here, and that you can construct the entire function from a series of polynomial function. Next, I wanted to talk about the graph of the power function. So if we were to, say, use a calculator on this, let me just pause this for a second and open up my calculator. Here, and we're going to go to the calculator, and if we try to graph, say, x squared, we see this this simple graph here. And then what happens if we increase the power with an even number? So say we go and we say y is equal to x to the 4th power, then we see the behavior of the graph is still the same. Both ends are going up, or any form of this graph we do y to the sixth power. The behavior of the end behavior of the graph still remains basically the same. Again, observe what's happening here. This also goes for graphs that have odd powers, such as say x cubed, and we graph it, we see the cube graph. Then if we were to make the power into x to the fifth power, the behavior of the graph still remains the same. The bottom end is going down, the left end is going down, the right end is going up. So that's what this is saying here, that if we start with the original graph and we do smaller powers, all it does is close in the graph, but the end behavior of the graph, both ends are still going up. And in this case, in the second case where odd powers, both the left end is going up, the left end is going down, right end is going up. Next, we want to discuss the zeros of the function. Here's a graph that shows a polynomial function with 4 x-intercepts. We call that a x-intercept are the points where the graph either cross or touch the x-axis, and these are marked on this graph. Consequently, the x-intercept is either the graph, when we consider intercept, the graph is either below or above the x-axis. Or above the x-axis. In other words, those intercepts either divide the graph into below, or it continues to be below here, and here it's above the x-axis. If a polynomial function is factored completely, it is easy to locate the x-intercept of the graph by solving the equation f of x is equal to 0, and this is called the zero product property, recall from algebra. All this is saying is that if I have, say, polynomial p of x is equal to x plus 3, x minus 5, then to find the zeros here, I would simply take x plus 3, set it equal to 0 to get x is equal to negative 3, and x minus 5, set it equal to 0 to get x is equal to positive 5. These are the x-intercepts. Now the thing this is talking about here, it says, for example, if we can see the zeros of the function of 1 and negative 5 here, based on this, the following statements are equivalent, where r is a point that crosses or touches the x-axis. R is sometimes called a real zero. R is called an x-intercept. And x minus r is a factor of f. And finally, r is a solution of f of x equal to 0. All of these are saying exactly the same thing, that positive 1 and negative 5 is a real 0, or an x-intercept, or x minus 1, x plus 5 is a factor, or we set this equal to 0, then positive 1 and negative 5 the solutions to this function. So here we're asked to find the zeros. So if we're finding zeros here, we would need to factor. Two numbers that multiply to give negative 3 and add to give positive 2. So x plus 3, x minus 1 is equal to 0. So the zeros are negative 3 and positive 1. This is already factored, so the zeros are, take x plus 1, set it equal to 0. And x minus 2, set it equal to 0. So x is equal to negative 1, and x is equal to positive 2. Now, there are times when we would be asked to find a polynomial of degree 3 whose zeros are given. To do this, you would probably want to take your function and set it up as binomial factors. So the factor that gave us negative 4 is x plus 4. The factor that gave us negative 2 is positive 2. And the factor that gave us 3 is x minus 3. And then you would want to go ahead and FOIL this out and write it in the standard form. So foiling x plus 4, x plus 2, we get x squared plus 6x plus 8 times x minus 3. And then go ahead and distribute this out. Distribute x first and then distribute negative 3 first. So we have x to the power 3 plus 6x squared plus 8x, and then distribute negative 3 to everything in the first parenthesis here. We have negative 3x squared minus negative 18x minus 24. Collect your like terms, and this will be your factored, your polynomial function. F of x is equal to x cubed plus we have 6x squared minus 3x squared, so that becomes plus 3x squared minus 10x minus 24. And if we were to graph this with our calculator, we would see the 3 zeros, negative 4, negative 2, and positive 3. So let's go ahead and put that real quickly into our calculator and observe the behavior of it. I'm going to clear these out. And we go ahead and put in the function here. We have x to the power 3 plus 3x squared minus 10x minus 24. And if we graph this, we could see that our intercepts are located at negative 2, negative 4, and positive 3, which is what we had in the original function. I'm going to go ahead and capture the screen and see if I can place it into the notes for us. Okay. Oh. Perhaps it might be better to put it over here. Let's put it over here and delete it from here. All right, never mind. I can't figure out what to do here, so we'll just leave it. Okay, here we go. All right, that's good. All right, now moving on. We have a definition of what's called the multiplicity. If we have, say, x minus r to some power m is a factor of the polynomial and of the polynomial f, and x minus r to some power m plus 1 is not a factor, then r is called a real zero. In other words, if r is a polynomial and the exponent of the factor that produced the root m is m, then we say that r has a multiplicity of m. For example, if we have x minus 4 to the power 5, the multiplicity is equal to 5. That's all this definition is really saying here, and it's just the mathematical form of the definition. Now, a couple of things about what this multiplicity tells us. If the sign of the multiplicity numerically, if the zero is even, such as x minus 4 to the power 2, then the sign of the function doesn't change, does not change from one side of to the other of r. Graphically, this means that the graph touches the axis of r. So we might have something like this, and the graph is simply touching here, not changing. So this occurs when that multiplicity is an even number. And then if we have a multiplicity that is an odd number, this is x plus 3 to the third power, in this case the graph, the sign changes, the y value changes sign, and the graph crosses the x-axis. So if we have something like this, and this part of the graph is going through -3, the y value, the f of x value, changes in sign from positive to negative, because this power here is an odd number. So the multiplicity tells you whether the graph crosses or touches the x-axis. In this case, we're asked to find the multiplicity, find the x and y intercepts of the graph, and then state the multiplicity. So we're going to notice immediately that if we set negative x cubed equal to 0, x minus 3 equal to 0, and x plus 2 equal to 0. This gives, we have 0, x is equal to 0, x is equal to positive 3, and x is equal to negative 2. So at these points, at each of these points, we can see the power is odd here. So the graph multiplicity is equal to 3. Crosses, in this case, the multiplicity that created this is even. Touches, and in this case the multiplicity is 1, which is odd, so crosses. So to find the y-intercept, we would simply set the function, set the x value equal to 0. So y-intercept set x is equal to 0. So y is equal to negative 0 cubed, 0 minus 3 squared, 0 plus 2 to the power 1. And since we're multiplying everything by 0 here, y is equal to 0 would be the y-intercept. Next, I want to show you how to possibly graph a function here. We see that we have two x-intercepts here. X is equal to 2, and because the power is even, it touches. And x is equal to negative 1. Because the power is odd, it crosses. The y-intercept, y is equal to, remember we set x equal to 0 for this, so 0 minus 2 squared, 0 plus 1, so this is equal to 4. So if we can put all of this on the graph, we would be easily able to sketch the graph here. We know that the graph touches at 2, crosses at negative 1, and goes through the y-intercept here. So there's only one thing that this graph can do. If it's going to cross at negative 1, it has to come down here. It has to go through the y-intercept, and then it has to touch positive 2. Okay? Crosses at negative 1, touches at 2, and crosses the y-intercept. Next, we would talk about the turning points. In turning points are places where the graph change, from a minimum to from decreasing to increasing, or from increasing to decreasing. In other words, where minimum and maximum points are located. An example of a turning point, of course, would be the vertex of a parabola. And in the parabola, the degree of the polynomial 2. And we know that a parabola only has one single turning point. In general, if the polynomial function has a degree n, then it has at the most n minus 1 turning points. And if it has n minus 1 turning point, then it has at least n, then the polynomial is of degree n. What this is saying is that if we have a polynomial such as f of x is equal to 4x to the 5th power plus 3x squared, and so on, where x to the 5th power is the highest power, then the degree is 5, and turning points, possible turning points is 5 minus 1, which is equal to 4. Or if we're given n turning points equal to 4, then the degree, let's take another example here. Let's say the number of turning points is equal to 3, then the degree of the polynomial n would be 3 plus 1, or 4, a 4th degree polynomial. In this case, to find the degree of the polynomial, we would multiply out first to get the leading term. To get the leading term, all we need to do is multiply -2 times x times x, and this gives -2x squared. So this is a second degree polynomial. Turning points equal to 1 turning point. Next, I wanted to discuss the end behavior of the function. So there are a couple of things that we need to consider. If using the leading term, use leading term, and if that leading term, let's say our leading term has a equal to, or a is greater than 0 and n is even, then both ends of the graph will go upwards. So if that leading term is something like 3x to the power 4, then both ends of the graph will be turned upwards. If a is a negative number and n is even, such as a -3x to the 4th power, then both ends of the graph will be turned downwards, like that. And it might, I'm making a space in between because it might have some turns in between. Then if a is positive and n is odd, such as 5x cubed, then the left end would be down and the right end would be up. Okay? The left end of the graph will be turned downwards and the right end will be turned upwards. And if a is negative and n is odd, such as -5x cubed, then the left end would be up and the right end would be downwards, like that. And you can probably observe this behavior in the with the calculator. For example, if I have y is equal to 4x to the 4th, 4x to the 4th power, this is a positive coefficient and an even power. If I graph this, I can see that both ends of the graph will turn upwards. If I changed it to negative 4x to the 4th power, I can see that both ends of the graph will be turned downwards. And if I change the sign to, say, x cubed, I could see that the left end is going down and the right end is going up. And if I place the negative sign in front of it by saying negative 4x to the power 3, then I would have, not sure what I did here, let me figure this out, negative 4x to the power 3, then graphed it, I would see that the left end is up and the right end is down. So that leading term, whatever that leading term is, tells us the end behavior of the graph. So let's go ahead and try to do an analysis of something here and see if we can apply what we know here. To find this, we can go ahead and actually graph this function here, given the information that we have, okay? So this here, the zeros are x is equal to -5, x is equal to -1, x is equal to +2, and x is equal to 4. Okay? The multiplicity is 1, 1, 2, 1. So crosses, touches, crosses. Okay, you can write in the multiplicity as simply the power of multiplicity 1, multiplicity 1, multiplicity 2, multiplicity 4. And then to find the general end behavior, we would simply find the power function, the leading term, by multiplying x times x times x squared times x. Which is x to the 5th power. So this being positive and odd means the left end of the graph will be going down, the right end will be going up. Okay. So -5, -1, +2, and 4. Okay, so this end is down, this end is up. In order for it to be touching here, it has to be this way. And it's crossing here. So in order for it to cross here, it will have to come down to some point on the y-axis, come up here, and touch here, and then turn again so it can cross here. So let's see if we got that right. Left end is down, right end is up. It crosses at -5, crosses at -1, touches at 2, and crosses at 4. By the way, the y-intercept here would be 5 times 1, -2 squared is +4 times -4. So this is 20 times negative, 5 fourths of 20 times -4, which is -80. So this point where it crosses here would be -80. All right, so we're quickly approaching this part of the graph. We're not going to cover this example. We're going to skip this one here. And we're going to look one more time at the steps, because in chapter 5.2 we will be actually graphing the effect function. So step 1 would be to determine the end behavior. Find the x and y intercepts, determine the zeros of the function, and whether the graph crosses or touches the x-axis, determine the maximum number of turning points, and use the information to sketch the graph. So we're going to do one or two more examples of using that. Analyze the polynomials. Step 1, to find the end behavior, we would simply use the power function here, or the leading term, sorry. The leading term is x squared times x, which is x to the 4th power. So it tells us that both ends of the graph are up, since this is positive and even. Next, we find the intercepts, the x-intercepts. X is equal to -4, -1, and +2. Here it touches, since the power is 2, crosses, and crosses. That would have been step 3. Step 4, since this is a 4th degree polynomial, turning points, number of turning points would be 3. And we also need the y-intercept. I didn't compute the y-intercept, so let's go back here. Y-intercept, set x equal to 0, y is equal to 0. So this is 4 squared times 1 times -2, which is -32. So we've actually got enough information to do our graph here. All we would need to do is to make up axis here. This doesn't have to be anything spectacular. And remember, both ends of this graph is going upwards. So we will mark the intercepts, -4, where it's touching. And if it's touching and this end is going up, then the graph can only do this, right? Touch. Then add -1 and a +2. And the y-intercept is at -32. So let's go ahead and sketch this graph. Remember, this end here is going upwards and touching here, and this end is also going upwards. So it touches, it comes up to some point, it crosses, it goes down to -2, and it crosses. We're going to cover the last example here. This is this function. So step 1, the leading term is -x squared times x to the 4th, x, which is -x to the 4th power, which is saying that both ends of the graph will turn outwards. And the intercepts